Hello and welcome. So in today's video, we're going to be going over topic 4.8, which is Newton's method. And of course, I'm going to have a lot of practice problems here, so if you just want to skip to that, I will maybe put a link to where it's at, or split this up. I don't know. I'm going to try something new today. Anyway, so I want to start by asking is how might we solve the function y is equal to cosine of 5x plus 3x plus 9x squared? That's a very big mess. We do not have a method for solving it. Well, Newton proposed a wonderful method for really trying to find the solutions for any function, really. And in fact, if I remember correctly, this is the method that our calculator, let's say you're using a TI-84 calculator, or any calculator in general, will use for approximating, let's say, the square root of a number. Alrighty, so how do we do this? Or what do we do here? Well, here's the big idea. Let's say that we're using a derivative. So we've used derivatives before for approximation. This is going to be the same thing. So we're going to say that this curve here is f of x. On this curve, there's going to be a point that's called xi. So there's going to be a point on this curve called xi, comma, f of xi. Well, we can then use this value as a way to approximate this tangent line here. So we're going to say y is equal to, y minus f of x of I is equal to is equal to the slope, which is going to be f prime of x of I, times by x minus x of I. Okay, well, this is just an approximation, but let's give this approximation a name. In fact, we're going to call this x2 after x of I. Well, now this approximation for the slope, we can use, or not the slope, but for the 0, we can now use this x of 2 as our starting point. So then we go y minus, and now we're here at this point, at x of 2, f of x of 2 is equal to f of x of 2 is equal to f prime of x of 2 times by x minus x of 2. Well, looking at this graph, what we're going to see here is that we're going to get this tangent line. And of course, I don't think that this is going to end up that approximate yet, so I'm going to just undo that line and maybe say that it's a small bit closer to there. Alright, so now we're at x of 3. Okay, so now we have y minus f of x of 3 is equal to f prime of x of 3 times by x minus x of 3. Well, we're going to keep going. Now we're going to use this x of 3 for the approximation. And what we see is these approximations are going to get closer and closer to the 0 of the function. And what we can do is we can actually derive a formula for this. Well, we know that our next x that we're going to choose, let's call this x of n, plus 1 is going to be equal to, we're going to add. So what I believe I want to do here, to kind of show you this general process, is I'm going to real quickly start over. So we're going to say that we have a function y minus f of x of n. Okay, and that is going to be equal to our f prime of x of n times by x minus x of n. Now what I want to do is I'm going to expand this out, or rather, I'm going to set this function equal to 0. Or we want to find when y is equal to 0. So we say 0 minus f of x of n is equal to, and we're going to expand this out so we get x times by f prime of x of n minus f prime of x of n times by x of n. Well, now what I'm going to do is I'm going to add this portion to the other side, so we get, we are going to get minus f of x of n plus f prime of x of n times by x of n, and that is equal to x times by f prime of x of n. So now dividing this f prime of x of n from both sides, we get x is equal to this negative f of x of n divided by f prime of x of n plus x of n. And rewriting this, we get x is equal to x of n minus, f of x of n divided by f prime of x of n. Well, what is this x value, you might ask? Well, it's going to be our next guess, so we call this x of n plus 1. And that is our general formula for Newton's method. So this right here is going to be our way of approximating values. So now this is this portion of the video that's now practice problems, so if you skipped here, good on you. So I'm going to ask, how might we want to approximate the value of pi? Well, what I'm going to do here is I'm going to find a function that is going to have a root of pi, or is going to be equal to 0, and x is equal to pi. And that function is going to be y is equal to sine of x. Well, now what we have to do is we have to get an initial guess for pi. So I am going to say that my first guess for pi is going to be x is equal to 3. Okay? Well, with Newton's method, we now have to say, x, and we're going to call the x1. Well, then x of 2 is going to be 3 minus f of x, which in this case is going to be sine of x, which in this case x is equal to 3, divided by cosine of 3. Well, now what we have to do is we have to use a bit of calculator practice, so this is going to take a moment. So if you plug this into your calculator, you're going to get an approximate value here of 3.14. Sorry, I accidentally wrote a 4 instead of a 1. 1425. Alright, now we're going to use this as our guess. So our x3 is going to be 3.1425. And I'm going to keep all the digits, hopefully, in your calculator, minus sine of 3.1425 divided by cosine of 3.1425. And for this value here, we get 3.14 159. All right, and what is the actual value of pi, you might ask? The actual value of pi is equal to 3.1415 and a few more decimal places. But you can see that this method is incredibly accurate within just a few shots, or a few guesses, really, for finding the roots, or the zeros of a function. Well, now we want to use Newton's method to approximate the following solutions. The issue here is we have two functions set equal to each other, but we want them equal to 0. So we're going to subtract over to the other side. So we get sine of x minus x plus 1 is equal to 0. Now what we have to do is we have to guess where this might be equal to 0 at. Or sorry, not 0. Well, yes, where it's going to be equal to 0 at. And for my guess, I'm going to guess, let's say pi, let's say a value of 2. X is equal to 2. So then our x of 2 is going to be equal to 2 minus sine of 2 minus 2 plus 1 divided by cosine of 2 minus 1. Alright. So, plugging that into our calculator, we get a value of, and for the solution, what we get is actually 1.93595, and then repeating that trial again, we get 1.9359, and I'm not going to rewrite out all the rest, minus sine, I'm just going to say that this is equal to a of a minus a plus 1, all divided by cosine of a minus 1. Alright. And interestingly enough, we get the exact same answer. So we've already found our root within 3 guesses. Well, now we have to find the derivative, or now we have to find the solution to the following function. Okay, so we subtract everything over to one side, like we did. So we get arctangent of x minus x squared minus 3 is equal to 0. Now I want to take the derivative of this so I can, yeah, like that. So now I want to take the derivative of this. So I get 1 over x squared plus 1 minus 2x, and that's our derivative. So now I'm going to say that I think this is going to be equal to 0 at a value of approximately approximately 1. So x, my first guess, is going to be equal to 1. So then my second guess here is going to be 1 minus arctangent of 1 minus 1 squared minus 3, all divided by 1 over 1 squared plus 1 minus 2 times by 1. Alright, well, let's plug this function into our calculator, and I'll be back in a moment. 1. Plugging the result in the calculator, we yield a result of negative 1.14306. And then plugging it in again, we get a value of negative 1.14306. And that is where the root is. So now we want to use Newton's method to approximate critical values of a function. Interesting. So what we have to first do is find the derivative so we can set the derivative equal to 0. Then we have to find the derivative of the derivative so we can use Newton's method to approximate the critical points. So what we're going to do here is we're going to say y. So y is equal to, I suppose there should be a y there, 6x minus x to the fourth plus 3x squared minus 2x. Alright. So then our y prime is 6x to the fifth minus 4x cubed plus 6x minus 2. Alright, taking the second derivative of that, we get y is equal to 30x to the fourth minus 12x squared plus 6. And that's our answer. So now what we have to do is we have to make a guess. So for our first guess, I'm going to say our guess is going to be x is equal to 1. Well, x of 2 then must be equal to 1 minus y of 1 divided by y prime of 1, which yields a result of. For first result, it's 0.75. For third result, it's going to be 0.75. However, this is an example of whenever there's going to be a reoccurring loop where the slope is not going to actually equal the tangent line for one reason or another. So what we're going to do is we're actually going to change our first guess here to be x1 is going to be equal to 0.5 instead, and we're going to see if that changes our result. Now plugging in, or trying to find our second guess, we get 0.5 minus y of 0.5 divided by y prime of 0.5. And this gives us an approximate result here of 0.359. Well, doing it again with the point, or let's call this value b this time, we get b minus y of b divided by y prime of b. So our answer is going to be equal. And whenever we run that, we get 3.59, which is the proper root of this expression. Alrighty, well, that's all I have for you. I hope you enjoyed and found this video informative. Have a